Dear Doctor, thank you for your speech. Now I call upon Manuel Nuno from Vapourtec Limited UK to deliver keynote talk on catalytic process under continuous flow, current trends and applications.
Thank you very much for the introduction.
Yeah.
Hello, everyone. My name is Manuel. I'm Vapourtec's Chief Scientific Officer, and I'm going to take today's webinar to focus on how to transfer batch processes into flow. So this is very nicely linked to the previous webinar we just listened. So the structure of this presentation, I'm going to start with a brief introduction of flow chemistry for a better understanding of what parameters we need to be looking at when we are taking a catalytic process traditionally done in batch and how to handle it in flow. So there are different ways, different strategies, and some work for some examples, and some others are more suitable for other types of catalysis. So we are going to cover photocatalysis, homogeneous processes, or yes, hydrogenations via heterogeneous catalyst. To start with, first things first, we are VaporTech, a UK established company, and we've been selling flow chemistry systems since early 2000s. So we have over 700 around the world in both industry and academy. And we have one of our best-selling reactors is a photochemical reactor, and I will explain a bit more in detail why photochemistry is such a trend in continuous flow, and we have more than 300 reactors being used worldwide. We try to become the most flexible lab equipment flow chemistry system. So the idea is that with our system, you can do the chemistry you want today or you want in 5 years. And that's why we have some customers, they do polymerization in flow, some others do hydrogenations or even peptide synthesis. So the aim is just to have different types of reactors that you can use in your flow platform. This is going to be very much linked to the parameters we need to look at and how to design a flow chemistry setup. So although there has been touched before, you might be aware what are the important features of flow chemistry. We have an excellent heat transfer, and this is simply because the surface area to volume ratio of flow reactors is much, much greater than any vessel or flask that you might be using to do reactions in the lab. We have high rates of mass transfer, so we can miniaturize and work with smaller volumes, and this allows us to have a precise control of reaction parameters, which is key for when we are doing, for example, lithiations. In flow, it's not uncommon to find lithiations done at 0 degrees C or minus 10 degrees Celsius instead of acetone and dry ice, and this is simply because we have a really good control of reaction parameters. We can work under pressure with no problem, so that makes very safe use of our systems to be going up to 250 degrees Celsius, for example, with volatile solvents. And this is one of the reasons why we can accelerate chemistry in flow. And just simply, if you need to have more product, you can really just run for longer the reaction and you will collect more product. So when we're looking basic setup on any flow chemistry system, it can be ours, it can be our competitors, or any bespoke system that any laboratory have developed. 3 key parts stand out. We need to have pumps, and this is the most important component. We need to be reliable and accurately delivering a flow rate, otherwise we won't be able to reproduce the experiment. And that's very tricky because all chemists prefer different reagents, so this pump needs to be compatible with a wide variety of chemicals. Then we need to have a reactor. This is a known volume where the reaction will take place. It can be heated, it can be cooled, irradiated with photons, or we can just pass current. Whatever activation energy is required for the reaction, it will take place there. And finally, we just need a back pressure regulator. So regulating the system pressure allows us to work over room conditions, so we can easily work at 10 bar, 100 bar, or 200 bar. That just being given by the back pressure regulator. And this is pretty much depending on the nature of your reagents. The rest is just ancillary add-ons that we just design our flow chemistry systems to make life easier. So as we have discussed before, chemists are not engineers and engineers are not chemists. So our aim was to develop a system that is a tool for chemists. So you don't need to know chemical engineering. You just need to know that our systems can pump reagent or solvent, so we minimize the reagent usage, and we collect the product as it comes out because we have an algorithm built in the software that predicts the dispersion. So you just can use the system as an extra tool that you will have in your lab. I mentioned pressure, and this is probably the best slide to summarize what's so important working under pressure and what we can achieve. This is a table that compiles the system pressure that each given solvent on each one of the rows needs to be to not evaporate effectively. So we are looking at the pressure in bar, and each column is a different temperature. So if we take, for example, butanol, because it's just the first one, the first row, if we want to work at 100 degrees Celsius, we just need 0.5 bar to prevent the butanol from evaporating. That's quite doable. If we want to take butanol to 250 degrees Celsius, we'll then need to have 24.1 bar on system pressure to prevent any butanol from evaporating. And as I said before, this is very simply done in flow because we can work under pressure. Imagine doing that in batch, you might be looking at a very expensive autoclave. And that happens with all the solvents. And this is the very same reason why we can push kinetics. It's simply increasing their activation energy. It allows us to reduce the residence time, and we can do it safely because we can work under pressure. If we want then to take it to the next level, we can start looking at multi-step reactions. So in this case, we have 3 reagents. We are making A plus B to give an intermediate that can be either unstable, toxic, or just moisture sensitive. And that reagent just reacts in line with the following reagent in a secondary reactor, and then we can have a multi-step reaction. This is a very simple setup I use in my lab. I'm not sure about you, but every time we use LDA, it's not very good quality, whereas BuLi, we can buy really good quality butyl lithium. So I tend to make LDA in situ. So yeah, simply have butyl lithium reacting with isopropylamine and hydrous solvents, obviously, and room temperature, 1 minute residence time, and we can make LDA in situ and can be certain that LDA is the strength that needed to be. And this is how we work with flow. So then we can add an aldehyde for some enol chemistry. And this is a good example of how you can make unstable species in flow in a very simple manner. And just to wrap up the benefits of flow chemistry, we can look at from the other side where our customers apply flow chemistry. Any highly exothermic reaction or very rapid reactions will always benefit from flow because we have much better control of parameters. And yes, personally, I think photochemistry and electrochemistry have taken, well, flow has taken photochemistry and electrochemistry to a very next level. It's just simply for the way we can run these reactions. They are highly reproducible, very repeatable, and very easy to do. So now I have given a brief overview and we've seen which parameters have to be taken into account for any flow setup. How can we translate this when we're thinking on catalytic processes? Well, there is not single approach to translate batch to flow, not even at VaporTech. My colleagues and I would tend to disagree on how to do it. But regardless of the strategy, there will always stand out, 3 questions will stand out. So what's the physical form of your catalyst? That's probably the most obvious one. This will define how we can handle catalyst. It's not the same to have a homogeneous catalyst or an insoluble heterogeneous catalyst. We need to be able to handle them differently because they just have different properties. What type of reagents are we using? As I said before, solvent and pressure are very much linked together to temperature. So this will help us to design how we are going to handle. So this will give us some idea what type of pumps we need, but will also some reaction parameters. Are we going to use ethyl acetate or acetonitrile, or are we going to work with DMF that can be heated at really high temperature with low pressure? This is where we need to consider our reaction scheme. And finally, and probably this is more relevant for these days, how is the reaction taking place? Is it a thermally mediated process, or do we just need to heat? Or is a non-thermally mediated reaction that we need to think of a type of reactor that will allow us to irradiate photons, for example? So from the rest of the webinar, we are going to try to answer these questions and give some examples and overviews of what it can be done and examples of how I did it. Looking at the type of catalyst, we can obviously group them in two main categories. We can either have a homogeneous catalyst that is in the same phase as reagents, and for the purpose of this webinar, we can just consider liquid homogeneous catalysis processes. And these are the most simple ones to deal with. They are liquid. Flow chemistry systems can pump liquids very simply. So this will be just pumped as a reagent. If we are looking at the solid phase, heterogeneous catalysts, there are different phases of our liquid reagents. Traditionally, people have packed them in a fixed bed column because it's very simple, it's very effective, and that's a really easy way to deal with solids. Flow chemistry usually not good with solids, but this has changed in the last years through some products we developed. But this is effectively like a HPLC column. We will have our solid packed in a column and our reagents will flow through. So this is how we'll have a contact of solid liquid phase. Looking at homogeneous catalysis, we can start planning our reactor setup, and we have few options how to design this. So we can go to the most simplistic approach, in which our catalyst and reagent are premixed in the same solution. So we are effectively mixing them together in one bottle or one vial. They are pumped through the reactor and then passes through a detector, and we can collect the product. This is a very simple approach. It's just you just need to make one solution, and you can evaluate residence time and effects on temperature on your process. Unfortunately, you will have a fixed stoichiometric ratio, so you cannot change your catalyst to reagent starting material because you have already made the solution. So to overcome this, we could simply have catalyst and reagent made in different solutions. So we are effectively pumping from two different solutions, mix them together, and the reaction takes place. Same way as before, but another multi-layer. This allows us to evaluate residence time and temperature as before, but we can also tune the stoichiometric ratio to substrate. By simply changing the relative flow rates, we can start working with the stoichiometric ratio as well as temperature or residence time. So this is a simple approach. So a while ago, we did some decarboxylative cross-coupling at VaporTech. So effectively, we wanted to take our carboxylic acid, our aryl triplet, react them with coin metal catalyst. So copper will promote, is ideal for the carboxylation. Palladium catalyst will promote the coupling step. Very simple. Both of them are soluble, so we could make effectively all of them in the same solution using an NMP as solvent, 170 degrees C. It's very simple. And this reaction still took a lot of time to complete. Traditionally, flow chemical reactions take less than 30 minutes. But when we compare it to what happens in batch, is that we preferentially remove the carboxylic group. So we achieved really good conversion in flow. And we decided to do a substrate scope. So I was saying that we can premix everything in one bottle and use one bottle to make our reactions. We can also make a variety of smaller bottles, so we can use a liquid handler to load different types of substrate. So this works in the same way as the HPLC sampling table. So you put your vial, an injection will absorb some of your reagent and will load it in a sample loop, and then the sample loop injects it into the HPLC column. Here is the same. We could use a sample loop and a liquid handler to start evaluating different solutions. So we can take this carboxylic acid, other substitution groups, and we can do the reactions in series. So because this is quite handy, as you just need to plan the reactions, press play and go. This is what we did. And within a day, we managed to evaluate a substrate of 7 different starting material carboxylic acids with kind of the same results. So this was a very easy and simple example of how we can work at 170 degrees, evaluate very quickly different substrates and in an automated manner. Then when we turn our eyes to the other type of catalysts, the heterogeneous catalysts, I said before, the traditional approach is pack them in a fixed bed reactor. Simple, yet effective, and this can work with any type of heterogeneous catalyst. We can put immobilized enzymes, Raney nickel, or even copper ferrules. Just pack them through and flowing reagents through. Very simple. But it's not always the preferred option. And at VaporTech, we work quite hard to develop a type of pump that could pump slurries. So we ask ourselves, is this the only way we can handle solids in flow? Solids tend to block the reactor, so we need to develop a type of pump that could pump slurries, but could also act as a back pressure regulator. So we develop a type of peristaltic pump that allows to pump slurries gases, and it can regulate the system pressure, so we will not block the reactor. Because something you need to consider is if you are putting something on a flow reactor, it will come out. So if we are not able to handle solids on the way out, if we're putting solids on the system, it will eventually block. So this is a very nice example for types of catalysts that make really nice slurries. Titanium dioxide is one of them, palladium on charcoal for hydrogenations, and I will give a bit more of example in the coming slides. Finally, the last type of heterogeneous catalyst we cannot forget is, well, what if the reactor itself is a catalyst? For example, click chemistry needs copper for the reaction to occur, and we develop some copper reactors that can take reaction. So we are actually having the reactor being the catalyst, and it works beautifully, but the same. Not all the cases have all the solutions. And to share an example of heterogeneous catalysis, I need to start with the Suzukimiara coupling. If any of you is a user of VaporTech, you will remember this reaction. This is our basic training reaction for anyone new to flow. It's a beautiful reaction because we have bromopyridine and phenylboronic acid react on a immobilized palladium catalyst, and we get the compound. Very simple way, but we can start tuning different reaction conditions and follow the results by HPLC. So it becomes a very interactive training. So in this case, we are taking palladium catalyst immobilized and put in a packed bed reactor. So we designed the system by having two channels. I was saying before, in this case, both reagents are going to be pumped separately. They will premix in a reactor, and the first tubular reactor is mainly just to bring all the reagents up to temperature. So we want to make sure that both catalyst and reagents are at the same temperature, and we can evaluate with confidence what's the impact of that temperature. And once they come out from the first reactor, they will pass through the immobilized fixed bed reactor, and the reaction will take place, and we'll be able to collect the product. So this is a very nice example to see what's the effect on temperature and residence time. So you can see here in the second entry, a 70 degrees C to achieve over 90% conversion, we need 5 minutes residence time. If we crack on the temperature to 100 degrees Celsius, we just need 90 seconds to achieve similar conversion. So this is one of the beauties of being able to work at high temperatures, because it just simply can be done safely. We can speed up the process, and by speeding up the process, we can do many more reactions. And I said before, if you want to just create more product, you just need to run for longer. So this slide just shows what's the effect on this very same catalyst over a longer run. We wanted to pump for over an hour and a half just to collect enough product to have as a sample in our stores. And we could follow the conversion and yield over these 90 minutes by just taking fractions and evaluate them by a HPLC. And you can see that, yeah, it dropped a bit, but it's nothing significant over a continuous process of 80 minutes, 100 degrees C. This catalyst just keeps going. And I mentioned before, we can pump slurries. So why should we thinking on pumping slurries if it's so simple to put your catalyst in a column? Well, there are two answers to this question. One of them is some materials like palladium on charcoal, they compact very well. And that can become a problem because the actual catalyst could pack so much that will generate high back pressure and will risk the experiment to stop. So what we can do as well is pump it as a slurry, and we can avert this problem. Another benefits of pumping slurries or catalytic slurries is just simply how much catalyst you can put on the system. If you have a fixed bed column fixed with catalyst, you know how much catalyst you have, and you know what's going to be your ceiling in terms of conversion. Whereas if you're pumping a slurry, you just can pump more, and the reaction just will keep on scaling up. So this is what we wanted to show in here. We wanted to show how you can pump slurries, how you can pump gas with the same pump, and how can you control the system pressure with the same type of pump so blockages do not occur. So we evaluated different palladium loadings, different slurry loadings, and we have achieved 16 experiments in under 12 hours, showing that, yeah, we had selectivity control, and we managed to cleave and get the oven seal vanillin to the desired API we wanted to generate. So how, from a technical point of view, how does this look? Well, we have 3 lanes. one effectively for each physical phase. So we have pump A, which will deliver our solution of O-benzene vanillin. Pump B will be pumping the slurry. So in this case, palladium and charcoal in ethyl acetate, it makes a really nice slurry. Problem is, if you anything in a bottle, you leave it to set, it will settle. So a technical tip is just use a magnetic steering on your reagent bottle, so your palladium and charcoal is under suspension all the time. And finally, we need to pump hydrogen. So we can just connect the hydrogen gas cylinder to our pump and meter standard cubic centimeters. So you can see in this diagram, we have A and B mixing. So we have our slurry with our reagent, then we mix it with hydrogen, and finally goes through our reactor. So another tip is when we use T pieces in flow chemistry, and when using a slurry, and the slurry channel shouldn't change direction. So if you're using a T piece, you should use the connections across and feed sideways your liquid reagent. And this prevents unwanted blockages or unwanted issues. Another benefit, we were working a 7-bar, and when we're delivering hydrogen gas, because we are under pressure, the gas bubbles were always pushed to saturate the liquid solution with hydrogen. So this is the reason we managed to achieve over 6 grams an hour of this API in what it is effectively a laboratory equipment system. So 81%, really good selectivity and really high throughput pumping as a slurry. So this is a nice example I like to show because it's a 3-phase reaction and we have really good contact in between all of these. So this reaction, yes, happens very beautifully. Okay, we have covered now the important bits of homogeneous and heterogeneous catalysis, but what happens when the reaction is not thermally mediated? As I was saying before, some reactions will need photons to occur, and we develop reactors that could take either immobilized photocatalyst, as you can see on the right-hand side. We can irradiate columns, fixed bed columns with LEDs. And we also have reactors designed for homogeneous photochemical reaction or pumping slurries, as you can see on the left-hand side. So this is our UB150 reactor, which is nowadays standard in photochemistry. And we developed in 2018, 2019, I believe, our electrochemical reactor. This is the ion electrochemical reactor that just allows to promote well, as the name says itself, electrochemistry. These two examples are traditionally quite difficult to achieve in bats, simply because we'll never reach a homogeneous radiation field in bats, and it will cause hotspots, and it's very difficult to reproduce with confidence. So photocatalysis, there's something I need to mention, and this is the same. Not all problems have the same solution, and in this case, there are a variety of photocatalysts out there. So from TBDAT or titanium dioxide, very typically 365 nanometers is where it needs to be irradiated to occur, to go for other fancy organic catalysts that can go up to 450 or even 500 nanometers. So with the same ethos of trying to develop a flexible flow chemistry system, we also wanted to develop a flexible photochemical reactor. And for that reason, we developed different UV sources. So we have a low pressure, medium pressure mercury lamp, ideal to deliver really energetic wavelengths like 254 nanometers or even 220. And for anything over 365 nanometers, we have really a wide range of LEDs that can deliver a precise, highly monochromatic wavelength for either standard or high intensity power. So one of the examples I wanted to talk about photocatalysis is the photocatalytic synthesis of gamma lactams, which happens with a hydrogen atom transfer catalytic process. So this reaction is very tricky to achieve in with thermally mediated reactions, multi-step, whereas in a photochemical approach, it can be simply done in one step. So you can see here, this is a system setup, very simple, but yet the chemistry is very, very complex. This work was done by the Creswell lab at University of Bath with one of our VaporTech flow chemistry systems, and in which they have effectively the aliphatic amine, methyl acrylate, catalyst, and an acid ion. They are irradiated under 420 nanometers and synthesize a gamma amino ester that can be cyclized to a gamma lactam. This process is very low or very poor regarding the photonic efficiency. The quantum yield is around 0.04. So this means that one photon will promote one reaction, but not all the photons you radiate will succeed. For quantum yields greater than 1, we are talking about cascade or radical processes. So under these conditions, they evaluated different substrates with other nitrogen functionalized groups and achieved the same result. And as I said, this photocatalytic synthesis of gamma lactams has a very poor photonic efficiency. So we develop a high power LED. So we have 54 watts of output power versus the traditional 18 watts output power we have. And the theory was that if it's inefficient photonic process, each photon will promote a reaction. If we double or triple the output or the photonic input to the reactor, we'll be able to double the conversion, because effectively the limiting step is the number of photons. And as you can see here, yep, double the photonic load pretty much means double the yield, followed by NMR. And this is a really nice example of what can be, we usually think about the starving reactions. It might be a reagent. In this case, is the photons. And to finalize this seminar, I wanted to go a bit more in detail on electrocatalysis and electrochemistry in general. It's becoming a very hot topic. We've seen a lot of interest because it can promote very green reactions. And we decided to develop an electrochemical cell that could work up to 5 bars, so we can pump gases or work at really high temperatures. And we wanted to make it flexible. So with over 20 different types of electrodes, you can very easily change the architecture of your galvanic cell, or electric cell, within minutes. So basics on electrochemistry. If it's so green, why people haven't using it more? Well, I personally think it's a process that's been held back by BAT's limitations. So any electrochemical reaction is simply a non-spontaneous redox reaction process driven by the flow of electrons across the solution. Why is being holding back in BATs? Well, BAT's electrochemistry is very tricky. It needs electrolyte all the time. It generates a non-homogeneous electric field that can generate hotspots in solution media. So now we are talking of competitive thermally mediated reactions and electrochemical reaction occurring at the same time. And this makes either really low efficient process or will lead to a very difficult purification. So what's bringing flow chemistry to the party, you will ask? Well, electrochemistry is we found electrochemistry the same approach as we did with flow photochemistry. By just having 2 electrodes sandwiched together very, very close to each other, as this diagram indicates, we can have a homogeneous electric field because both electrodes are at the same distance and both electrons are always on contact with the same solution. So now electrolyte is an option. The electrodes are so close that we don't need to add electrolyte. We can make a more green process. And we are always able to control the temperature and will be achieve a homogeneous temperature across the reactor, whereas in BATs, we have the risk of having these hotspots. So this will allow effectively, and I believe this will happen in the future, to switch from organic oxidants such as PCC for some alcohol or aldehyde formation by just using methoxylated electrochemical processes. In 2019, we this is our last example of today. We were inspired by a paper published by Pfizer. They were doing an electrochemical cross-coupling of organic halides. So this was a reaction they wanted very simple to couple, but in a very novel way. We were using a nickel electrocatalyst. And this nickel electrocatalyst, what happens is it will reduce in the cathode. So it will go through all the nickel electronic species, and that will be the catalytic cycle. So what decided to do was, as I said before, a simple approach of homogeneous catalyst. We can mix all the reagents in one solution because if there is no current, the reaction won't happen. So we just set several reactions passing across the same reactor. So we wanted to evaluate what's the effect of the ligand. Is temperature an impact on electrocatalysis, or residence time is going to be critical for this process? So we decided to evaluate different reaction conditions from running at room temperature up to 50 degrees C. And we found that, temperature and residence time had a big impact on the conversion to the desired molecule. But what we found was the type of ligand, in this case, had the most dramatic impact. So we have L1, that is an amidine-based ligand, at both 10 and 20 minutes residence time, outperform any other flow condition we tried. Well, this is the end of my presentation. Thank you very much. If you have any question, I'm more than happy to ask, or if you want to reach me out later to discuss more chemistry, we are always happy to talk about science and what problems you have and how they can be solved in flow. So yeah, thank you very much.
Yeah, any questions?
Yes, this is Eric. Go ahead, Javier.
Yeah, thank you. So thank you for the presentation, very clear. I would like to ask, because there is a lot of tendency now of combining flow chemistry with machine learning as well, and also to combine everything together. So it's a field that you are also considering for the future and collaborations?
So that's a good point. Thank you very much. Yeah, it's something we still do. We started doing it a couple of years ago.
Okay.
So what we have is our system can be interconnected with, so usually MATLAB, or people use LabVIEW to insert the self-learning or self-optimized algorithm, and that will be driving our flow chemistry system. So effectively, let me go to so this system can be controlled via an independent software. And this is how we'll be able to run self-optimized process. So you need a type of analytical technique, can be Raman or can be UV that we can easily implement, or can be HPLC. So the self-optimized software will learn or will evaluate that result and will implement the next reaction conditions. And there are a lot of papers that have been using it, and yeah, it's just fascinating. And we are getting this question more and more every day.
Okay, thank you.
This is Apurvo. I have a question. On the decarboxylative coupling, I noticed you got one of the byproducts as loss of metals, basically hydrogen substitution product. And your carboxylic acid has a proton. And when you metal it, that carbon for coupling, that carbon metal bond can pick up the proton from carboxylic acid itself. So can you do the same chemistry with not carboxylic acid, but the carboxylate salt?
Wow,
But there is
proton involved. We did not try. That's the short answer. But I don't see why you shouldn't.
Yeah, this is Eric. Just wanted to ask you about your application with slurry flow. I mean, that is the standard problem with slurry, is you have to be able to separate the catalyst from your stream and reuse the catalyst. So it is that is why fixed beds are so much easier to use. Is there an option for this type of reactions where you can have, instead of having a very fine particle size for the slurry, where you can have a highly dispersed fixed bed? I mean, platinum is very easy to disperse. So your life would be a lot easier when you don't have to deal with plugging and having to shut down often. So is there an option where you can have a highly dispersed metal supported on a fixed or on just any standard support?
Yep.
Versus the slurry.
So yeah, no, we do. So this type of packed bed or fixed bed reactor, it comes in different sizes. So we can use a standard small 2 millimeter internal diameter, which is few milliliters, or we can go to a really big one, which is 15 millimeters internal diameter, and I think it's 4 times or 5 times the volume. So yeah, we can use a highly dispersed catalyst, And effectively, we just need a bigger reactor to accommodate the same loading if we want to compare in that way.
Yeah, I'm having a little bit of conflict with the scales because I work in oil refining, so our scales are more like 3 meters by 30 meters. So I think that some of the problems that are encountered now in pharmaceuticals have